Today we're talking about calorimetry and molar enthalpy. So let's just get into and figure out what these things are. Calorimetry. Think about a chemical process as a system. Or we're going to call it a system, but let's think about it in like this diagram here. It is going to be surrounded by other stuff. Glassware, solvents like water, your hand. Everything that's not part of the system, the actual chemical process, is part of the surroundings. Energy can go from the surroundings into the system. Energy can also go from the system into the surroundings. And what we are able to do is measure the temperature change of the surroundings. What we want to do, and what we're going to be trying to do today, is connect that temperature change of the surroundings to the energy change of the system. So that's our whole job today. We're going to use specific heat capacity. Now, you don't really need the definition here, but I do want you to understand the specific heat capacity is A, fairly unique to every individual material, B, based on its amount of mass. Now, that should make sense. If I have a small amount of water, it's going to be easier to warm up than if I have a large amount of water, using water as my example. Mathematically, taking those words and turning it into a mathematical expression, you don't need this either, not really, is here. Specific heat capacity equals energy divided by mass over temperature. We're going to rearrange it most often, and we're going to use it in this because what we want to do is use it to find the energy. So if I know the specific heat capacity of water, and I know the mass of water, and I know the change in temperature of water, all are either look-upable or measurable, then I can figure out the amount of energy. Now, remember that this is about the surroundings. We need to know about the system. So the connection is going to be a couple of things. The first connection is whatever energy was lost by the system, or gained by the system, was, well, let's go with lost by the system, was gained by the surroundings. Energy goes from one to the other. Mathematically, it looks like this, where one is on the plus, the other is on the minus. So to make them equal, properly equal, I change the sign of one of them. Does it matter which one I change the sign of? No. So don't get too committed to that form of it, because we're going to modify it in a few minutes. And then what I know about the surroundings is, if it's water or anything really, then specific heat capacity times mass times the change in temperature. So I'm going to eventually use this form where the energy of the system is taking the energy of the surroundings, specific heat capacity times mass times change in temperature, changing the sign. Again, don't get too committed to that because we're going to modify it slightly in a moment. Okay? That's what we know about calorimetry. Calorimetry then is measuring the temperature change of a sample of water, which is the thing we're going to use most often, and using that in that formula I just showed you to figure out the energy change of a system. Enthalpy change is if I were to standardize that or extrapolate that out to a mole. So if I were having 1 gram of chemical system versus 10 grams of chemical system, the amount of energy change, the temperature change would be different because the amount of stuff is different. But if I relate it back to moles, they should be the same. Okay, what does it even look like? So I'm going to have a data table, and I want to point out a couple things about this data table. Number one is I have a volume of water and I have a mass of solute. However, the solute, the lithium bromide, that is part of the system, and I start all this process with the surroundings. Second thing I want to point out is that if the surroundings is everything else, water, containers, your hand, even a thermometer, we're going to have to cheat a little bit on this one and ignore a lot of that stuff that we cannot get a full picture of, and we're just going to work with water. However, if you want to be really, really precise, you do have to consider some of those other pieces. Okay, I'm going to start with this. Now you'll notice how I modified it. Most of my math work is on the right-hand side of the equation, so I'm going to leave the negative sign on the left-hand side just for it to hang out there for a bit. Okay, so the energy of the surroundings was the specific heat capacity times mass times change in temperature. Now you notice it says mass, but I don't use the mass, the most obvious mass that's up there, because that's the mass of the system, not the mass of the surroundings. Water has this fantastic property where 1 milliliter has a mass of 1 gram. So 10 mils, 10 grams. Specific heat capacity of water is also 4.18 joules per gram per degree Celsius all the time, every time. You don't need to memorize that at this point. It'll be given to you almost every single time. Okay, running those numbers, yeah, I get that number of joules. Okay, now that is the negative, right? So I got to remember to flip that sign over. So the system lost 146.3 joules. Okay, but that was for a small amount, 0.5 grams. What would that be for a mole? Well, I need to know how many moles I'm working with. So the number of moles is mass divided by molar mass, giving me a fairly small number of moles, which means my energy divided by the number of moles is that. Now, at this point, that's a very large number of kilojoules per mole, so I'm going to turn that, joules per mole, so I'm going to turn that into kilojoules per mole. That would be a huge number of kilojoules per mole. Okay, and that's really all there is to it. So it's a fair bit of number crunching, really what it comes down to. Okay, what if there are two reactants, right? And which one do I use? And the answer is dealer's choice. You get to pick which one you want. I'm going to pick which one I want on this one, or it's going to suggest it in the question itself. So here, you're suggested to use hydrochloric acid, HCl. Similar kind of table, a little bit larger because now I've got more information. I've got a volume of acid, I have a volume of base. All right, pause here. Acids and bases are solutes, system, dissolved into water, surroundings. So the volume of acid and the volume of base is almost entirely volume of solute, nope, take that back, solvent, surroundings, that's easier, with a tiny little bit of solute, which means I can still use 1 gram of liquid stuff. One gram of water stuff is 1 milliliter of water stuff is 1 gram of water stuff. And I can kind of ignore the contribution of the acid and the base in the specific heat capacity. Anyway, similar starting point. Okay? Specific heat capacity of the surroundings times mass of the surroundings times temperature change of the surroundings. That still water-based, so all those numbers work. I get a number of joules. Flip the sign back over. Now, when I go to do the molar enthalpy, well, I've got a solution. I've got a concentration and a volume, but I had 2 volumes. Okay, now I'm going to go back to the first one because it was that was the acid. It was that volume and that number of milliliters. That volume and that concentration. So that would give me the number of moles, volume times concentration. Okay, small number of moles again, and then I take my total energy divided by number of moles, and I get a certain number of joules per mole, which is more convenient to express in kilojoules per mole, which is pretty much all there is to it. Okay, that's it. That's what calorimetry and coming up with molar enthalpy is all about. Using molar enthalpy, a little bit different, but calorimetry is going to be the same. Anyway, we'll talk to you another time.